Good Saturday afternoon to you guys. Sorry I didn't put this up last night, but I got a little busy and my throat was a little bit gone. Today I'm going to talk about how to graph rational functions. Okay, now we've been dealing with the rational expressions up to now in this chapter, and now we get to apply some of those skills in graphing. Ladies and gentlemen, all a rational function is a function where you'll have a polynomial on the top divided by a polynomial on the bottom. Now, if you need to look back to your notes on what a polynomial is, you might want to do that, okay? Now, the first part, before we can actually look at the graphs of a rational function, we need to look at some of the important characteristics of it. Now, one of the first ideas that's going to be new to you is something called a horizontal asymptote. A horizontal asymptote is a horizontal line. So this word line must be a synonym for the word asymptote and vice versa. An asymptote is just a special kind of line, all right? It's an imaginary line. In this case, it's a horizontal line that represents the y values that the graph approaches as you head towards infinity or negative infinity on the x-axis, okay? Now, let's take a look at why horizontal asymptotes are created when I have a rational function. Well, to start with, I'll tell you that there are three cases of horizontal asymptotes. The first case is when the function is what we call bottom heavy. The bottom heavy just means that the degree of the denominator of the polynomial in the denominator is bigger than the degree of the polynomial in the numerator. Okay? Well, the horizontal asymptote, or as I call it, ha, will always be y equals 0. Let's take a look at y. All right? Suppose I have this function right here. Right? I've got f of x equals x plus 2 over x squared minus 4. Well, again, if you think about it, the degree of the numerator is 1. The degree of the denominator, as you can see, is 2, right? Now, if you think about just mathematically what's happening here, to produce these y values on the graph, aren't I plugging numbers in for x and figuring out what y is? Isn't that how we always determine a graph? Well, if you think about it, as I put really, really large numbers in for x and simplify, what happens to the overall fraction that I'm looking at, right? Well, imagine this. Let's suppose I'm going to put in, and this isn't really even a big number. Let's suppose I put 1,000 in for x on the top and 1,000 in for x on the bottom. I get 1,000 plus 1,000 plus 2 in the numerator, or I get 1,000 squared plus or minus 4 in the denominator. Well, again, as these values of x get so large, would you agree the 2 and the negative 4 are inconsequential, really? Right? So these plus 2s and minus 4s, they don't even care. They don't even matter because the x's are what's getting really, really big. Okay? Now think about it. If I just look at the leading terms, the 1,000 on the top and the 1,000 squared on the bottom, who's growing faster, the top or the bottom? Well, would you agree that whenever you square a number, it grows really fast compared to leaving it alone? In fact, if you think about even just a small number like 1,000, right? You get 1,000 over, well, wouldn't that be 1,000,000 when you square 1,000, right? And can you see just with the number 1,000? Heck, I think I even make $1,000 in a year, so we know that's not that much money, right? Would you agree that 1,000 over 1,000,000 is very, very small? Well, imagine plugging in an even bigger number for x, right? Well, would you agree that if I plugged in, say, 1,000,000 for x on top and bottom, that bottom would be growing so fast that eventually this overall fraction would have to be approaching a value of 0. Now, can it actually reach 0? Well, you think about that on your own, okay? But we know that it'll always get closer and closer and closer to 0, right? Well, what if I plugged in a negative number for x? In other words, what if I plugged in a really, really big negative number, like negative 1,000,000? Well, would you agree that you would get negative 1,000,000 on top over negative 1,000,000 squared as a positive? Now, I know this fraction will be a negative, But ultimately, wouldn't that negative fraction still be really, really small? And still, again, it would get really, really close to 0. Okay? So here's what we say. If you ever look at a rational function where the denominator's exponent is bigger than the numerator's exponent, we know that the denominator will be growing so fast compared to the numerator that the overall y value, and don't forget f of x is a y value, would be approaching 0. So that's why we say that the horizontal asymptote that represents what my values are getting closer to is y equals 0. Now let's take a look at the second example. The second case is when we have an equal degree. And that means that the degree of the exponent on the top, or the degree on the denominator equals the degree of the polynomial in the numerator. All right? Well, in this case, the horizontal asymptote will be y equals a over b. Now, what are a and b? Looking back at the very beginning definition, a and b are just the leading coefficients of the two polynomials. So it's the leading coefficient of the numerator divided by the leading coefficient of the denominator. So it's just that ratio there. Okay? So let me take a look at an example of one where we have equal degree. Again, f of x equals 4x squared minus 9 over 3x squared minus 2x minus 8. Again, my degrees are 2. Right? So I'm squaring the biggest, the biggest thing I'm doing is squaring the values of x. Well, would you agree that squaring an x is much more powerful than subtracting 9 or even multiplying by 4? Right? Especially as I plug really, really large numbers in for x, like a billion or Brazilian or something like that, right? So I know that the most important part to the polynomials is the exponent, but in this case, isn't the exponent on the top growing as fast as the exponent on the bottom? So really, the exponents are equal, are doing the equal amount on the top and the bottom, so those kind of cancel each other out. So who's growing faster, the top or the bottom? Well, wouldn't the next operation after exponents help me determine that? Well, does it make sense that multiplication will be your next biggest operation? So in the numerator, I'm multiplying by 4. In the denominator, I'm multiplying by 3. So would you agree that this function is growing at a rate of 4/3? Right? So we would say that the horizontal asymptote for this function, I know that my y values would be approaching 4/3 as I get really, really big in the on the x-axis, either in the positive infinity direction or the negative infinity direction. Okay? And then lastly, we've got top-heavy. Folks, if the degree on the top is bigger than the degree on the bottom, then there is no horizontal asymptote. Let's take a look at y. Again, would you agree, since the numerator is growing faster than the denominator, as I plug in really, really big numbers for x, if I have a million on top, oops, squared over just a plain million, and again, in the grand scheme of things, a million's not even that much. I have that many hairs probably, well, maybe I don't have that many hairs on my head, but you know, you get the idea. A million squared compared to just a million, this top is growing really fast compared to the bottom, right? So there won't be a y value. In fact, we say that this graph, I know, will shoot off towards infinities in the positive infinity direction and in the negative infinity direction. You can either shoot up or down, okay? You'll explore more of the top-heavy scenario next year in pre-calc and then again in calculus, all right? All right, so in this case, if you ever see that the exponent on the top is bigger than the exponent on the bottom, we say there is no horizontal asymptote, okay? All right, mucho bien. All right, so that's the characteristics of the graph with respect to y. Now let's look at some characteristics according to x. All right? Representing domain restrictions on a graph. Now, we know domain restrictions coming out of what we were just doing with the rational functions with fractions and rational expressions of fractions, adding, subtracting, multiplying, dividing, and stuff like that. We know what a domain restriction is. It's a value of x that makes our denominator 0. Okay? Well, there are two types of domain restrictions in these functions. One is called a hole, and the other is called a vertical asymptote. A hole is a value for x which makes the denominator 0, but they get canceled out from the top and bottom when you simplify the fraction. Okay? Let's take a look at what I'm talking about. Suppose I have this guy right here. Well, would you agree if I simplified this expression on the right, I'd get x plus 2 on the top. That doesn't simplify, but at the denominator, I can factor that into x plus 2 and x minus 2. Would you agree that x plus 2's cancel, right? Well, would you agree that this x right here, I know is a domain restriction, because again, we always find our restrictions before we simplify, right? I know that x can't equal negative 2 is a restriction, right? But in this case, this x equals negative 2 will create on a graph what's called a hole, okay? And a hole is exactly what you think of. It's an empty looking point, right? Now, this will be the x-coordinate of my hole. How will I find the y-coordinate of the hole? Well, all you do is you take this x-coordinate and you plug it in to the simplified function to find your y value. All right? So take a look at this. If I have x equals negative 2 is my x-coordinate, to find the y-coordinate, I'm going to go f at negative 2 equals, well, since this is 1 over x minus 2, if I plug in negative 2, I get 1 over negative 2 minus 2, so negative 1/4. So I know that the hole will be located at the point negative 2 comma negative 1/4. And that's how you find a hole, okay? All right. Now, the next definition is called a vertical asymptote. A vertical asymptote is an imaginary vertical line. Again, here's this word asymptote again appearing. Again, it's just a special kind of line. This time, this vertical asymptote is a vertical line that represents values that make the function undefined that didn't get canceled out from the rational expression. Okay? Now, I call these vertical asymptotes like an electric fence. Your graph cannot ever touch a vertical asymptote because that graph is undefined at that value. Okay? And that's the purpose of it. All right? Well, if you think about that function we were just dealing with, would you agree that after I've got the simplified fraction of f of x equals 1 over x minus 2, what value didn't get canceled out of the denominator? The x minus 2, and therefore x equals 2, right, would make this fraction become undefined. This will be where my vertical asymptote is. X equals 2 will be a vertical line that I cannot touch when I go to graph the rational function. All right, again, let me repeat that. This did not get canceled out of the fraction when I was simplifying. That value that you get when you solve that, what's left, makes a vertical asymptote. All right? Now, notice, by the way, you always need x equals because it is an equation of a line. Now, together, the holes in the vertical asymptotes are what create my domain restrictions. Your domain will be everything but the x value of your hole and of your vertical asymptote. All right? So, I know that my domain is everything, all reals, except, well, let's see, didn't we get negative 2 and positive 2? All right? Now, hopefully that makes sense. Why can't I plug negative 2 and positive 2 in for x? Because in the original function, that would make a 0 in the denominator, which makes the function undefined. Now, in interval notation, if you think about a number line, remember going back to interval notation, if I plug in negative 2 and positive 2, circle, circle, I know that x can't be either of these values. But is it allowed to be everything else? Yes. It's allowed to be everything to the left forever, everything between the negative 2 and positive 2. A lot of times people forget that interval that it's allowed to be, and everything to the right of negative 2 and positive 2. Okay? So I've got 3 different intervals for my domain. It would be from negative infinity to negative 2, parenthesis, yin, parenthesis, negative 2 to positive 2, yin, parenthesis 2 to infinity. Okay? And what that says is your domain is everything, is all reals except negative 2 and positive 2. Okay? But again, your domain is always everything but the x value of the whole and of the vertical asymptote. Okay? All right. Now, folks, whenever you're doing this kind of work to create a graph, we always want to figure these things out in this order. Always find your horizontal asymptote first, your hole second, your vertical asymptotes third, and your x and y intercepts last. Now, I'm not going to go over how to find the intercepts because you know how to solve an equation to find an intercept. Now remember, always use a simplified fraction to find everything but your horizontal asymptotes. Yeah? You can use the original equation for the horizontal asymptotes, but nothing else. All right, let's put it all together to actually create a graph. Now, in this example, it says graph each function. State the horizontal asymptotes, the holes, and the vertical asymptotes. Find any x-intercepts that exist, okay? Now, I'm going to go back to this problem that we were dealing with before. So, because I know how you guys don't like the really long, exaggerated screencasts. All right, so we said, let's think is, all right, for the first thing, I got to find the horizontal asymptote. Well, because it's bottom heavy, I know the bottom's growing faster than the top. I know eventually as this graph gets bigger and bigger on the x-axis, my y value will approach y equals 0. So I'm going to have a horizontal line at y equals 0, okay? We said that holes are values that get canceled out of the numerator to the denominator that make the denominator 0. Well, again, we said x plus 2 over x plus 2, x minus 2, right? The x plus 2's get canceled out, so negative 2 is where my, x equals negative 2 is where my hole is located, right? And then to find the y value of that, we plug negative 2 into the simplified fraction of x minus 2, and we get negative 1/4 for y. So we said the whole value will be at negative 2 comma negative 1/4. All right? The vertical asymptotes are values of x that do not get canceled out that make the denominator 0. So x equals 2 is where my vertical asymptote is. And my domain is everything but where my whole x value is and where my vertical asymptote x value is. So it would be from negative infinity to negative 2, yin yin negative 2 to 2, yin yin 2 to infinity. Okay? Intercepts. To find an intercept, I know that I've got to plug 0 in for x to find my y-intercept, and 0 in for y to find my x-intercept. Okay? Now I'm going to do that again up here. My simplified function, remember we always use a simplified function to find intercepts. Okay? To find my y-intercept, wouldn't y equal just 1 over 0 minus 2, so negative 1/2? So I know my y-intercept is 0 comma negative 1/2. And my x-intercept, to find my x-intercept, I plug 0 in for y this time and solve for x. I would get 0 equals 1 over x minus 2. Well, wait, to get this x out of the denominator, wouldn't you cross multiply him across? And 0 times x minus 2 just becomes 0. So you get 0 equals 1. Well, that doesn't make any sense. Well, when things don't make sense, that means there's nothing there. So there are no x-intercepts. Okay? So I know he's going to cross the x-axis. The y-axis is 0, negative 2. 0, negative 1/2. But he will not cross the x-axis. Actually, and that kind of makes sense because I know I'm going to have a horizontal asymptote at y equals 0. This year, you will not touch the horizontal asymptote. He'll be a fence that you cannot cross. Next year in pre-calc, though, and in calculus later on, you will have some horizontal asymptotes that you will be able to cross. All right. Now, let's put all this information onto the graph. How do I do that? Well, luckily, I've got a graphing wizard to help me do this. This is the new Smartboard wizard. Let's see what he has to say about how to graph this, okay? All right, let's take a look here. All right. To graph a rational function, the first thing he says to do is to draw your horizontal and vertical asymptotes. So I've got one at y equals 0, okay? So that's just right down the x-axis. I've got one at x equals 2, so coming in here at x equals 2. So I've done that. Now it says plot any holes and intercepts. Well, I've got a hole at negative 2, comma negative 1/4. Now again, this is just a sketch of the graph. So at negative 2, negative 1/4, be like right there, I'm going to draw an empty circle. My graph has to go to that point, but it will not be filled in. It can't actually be that value of x. Do I have any intercepts? Yeah, I've got one intercept. I've got a y-intercept of 0 comma negative 1/2. So about right there, right? Now, after I've done that, I need to sketch my branches of my rational function using any holes and intercepts that I've created. Now, here's the thing. I know that I've got 4 regions. I've got 1, 2, 3, 4 regions on this graph. I know that my graph will exist on both sides of this vertical asymptote. I need to draw a branch to the left of this vertical asymptote and to the right of this vertical asymptote. Okay? The question is, will my graph be in the first in the first region or in the third region? Will it be in the second region or in the fourth region? Now, if I draw a graph in the first region, it cannot be in the third region. Well, and if you think about it, the reason is it would break the vertical line test. All right? Now, let's take a look at how we can determine what region to sketch in. Okay? So, here we go. Ready? Well, would you agree? Well, I've already determined that on the left-hand side of my vertical asymptote, I've got a point here and a hole here. I know that the branch on the left side must go through these points and hug your asymptotes on each side. When you draw your branches, always hug your asymptote. Remember, I'll ask you, have you hugged your asymptote today? All right. So I've got my branch on the left side of the vertical asymptote. I know that I can't have anything up here because that would break the vertical line test, right? So I've determined the left branch. Now I've got to determine the right branch. Well, in the last idea, if necessary, if I still don't have all my branches sketched out, I might have to pick a value on the side of my vertical asymptote that doesn't have the branch developed yet. Okay? So, to get my branch on the right side, I'm going to pick any value to the right of x equals 2, like x equals 3. I'm going to go back up and I'm going to plug 3 in for the x value in the simplified function. When I do that, I get 1 over 3 minus 2 is, well, that'd be 1 over 1, so 1. So I know that to the right of the vertical asymptote, the point 3 comma 1 will be a point on this branch. And by determining that, I know that the branch on the right side of the vertical asymptote is above my horizontal asymptote. I come in, I hug my asymptotes going both ways, and that is the graph of the sketch of a graph of a rational function. Notice how I said, would you agree that both ends, as they approach infinity, the y value approaches 0, okay? We'll play around with our graphing calculators with this next week. All right, and finally, on the last step, what are we going to do? We're going to call it a day. It's a day.